Well, we've just explored the chemistry of the water in the ocean, and in fact the special properties of the water molecule in terms of chemistry and salinity. And so now what I'd like to do is turn to the physical properties of water and discover that there are even more unique and surprising features about this simple thing, the water molecule, that are responsible actually for the very existence of a liquid ocean and a stable environment for life on our planet. So let's ask the question again, what's so special about water? Well, for one thing, water is the only substance that exists in solid, as in ice, liquid, and gaseous, as in water vapor, states at Earth's surface conditions. So nothing else really has this property of going back and forth between all of its individual physical states. The heat capacity, as we'll see in a second, is very high for water, and that's going to have an important implication for Earth's surface temperature. And solid ice, as I will show you in just a few minutes, is really unusual in that it's less dense than liquid water. And finally, light can only penetrate a limited distance through water. These are the key physical features that are going to dominate how the ocean governs the environment on the surface of the planet. So let's take up heat first. First of all, let's make sure we've defined the term. Heat is simply a measure of energy. Heat, in fact, is defined as the total amount of energy stored in some substance as actually random vibration of a quantity of atoms and molecules. Maybe you remember that the physicist's definition of heat is just the vibration of the individual bonds in given molecular structures or the vibration of individual atoms themselves. Temperature is something different, and it's very important to keep the concept of temperature and heat a little bit separate from each other. Because temperature, the thing that we can measure with a thermometer, is a measure of this stored energy specifically through the object's response in terms of changing vibration state to input or removal of heat. Now in just a second, we'll see why that distinction is actually important. Finally, one more basic property I want to define is something called the heat capacity. Okay, the heat capacity of any particular substance is specifically a measure of the amount of heat required to raise the temperature of 1 gram, by definition, of that substance by 1 degree centigrade. So heat capacity is the linkage between energy, heat, and temperature, the measure of the heat. And that's a little bit of a confusing concept. But so, for example, for pure water, 1 calorie measures 1 calorie raises 1 gram of pure water 1 degree Celsius. That's in fact how we define all of those individual things. Oh, and by the way, as an aside, the calories that you consume in food are actually kilocalories in the metric system. So there are 1,000 of the kind of calories that I'm talking about now. Well, let's ask a little rhetorical question then. If we think about 2 containers of fluid, which one contains more heat? A single cup of tea that maybe has a temperature of 150 or so Fahrenheit, maybe 70 degrees C, steaming away, or the Arctic Ocean. The Arctic Ocean with a temperature of 40 degrees Fahrenheit, or even less, something around 4 or 5 degrees C. Well, of course, one is a lot hotter. It has a higher temperature, that's the cup of tea. But the one that contains more heat by far is the Arctic Ocean, because it has many, many, many grams of mass, and so even though it's at a low temperature, it contains a very large amount of heat energy because it's the entire ocean. Well, the thing about water is that compared to other common substances, especially liquid substances on our planet, water has a tremendously high heat capacity. It can absorb or release a lot of heat while not changing very much at all in temperature. The heat capacity of water, that 1 degree per calorie per gram, is 3 times the value for something like ethyl alcohol, and it's many times the heat capacity of metals, which actually change in temperature quite a lot with the addition of a small amount of heat, or most other sort of common objects. Virtually everything has a lower heat capacity than water does. So what this means is that water is sort of inured to changing in temperature. It takes a lot of energy to move its temperature up and down a lot. Now, there's one more complicating factor with heat that we have to take up when we're thinking about water in the ocean or in fact any water. And that is that there are two different forms of heat. One that we're very used to and is very common, and another one that we don't think about so often but is actually equally important. So we think about heat as either sensible heat or what's called latent heat. Now, sensible heat is exactly what you think of when you think of a change in temperature. It's the amount of heat that you can sense, meaning sense with a thermometer, let's say. It's the heat absorbed or released during any change in temperature. Latent heat, though, is the energy, again, the heat that must be absorbed or released to change the state of some material from liquid to solid or liquid to vapor. So, for example, freezing or evaporating water requires the input of a lot of latent heat and doesn't necessarily change in temperature at all at that time. Let's look at that in a little bit more detail because it's a little bit of a confusing concept. So the sensible heat for changing the temperature of water is simple, 1 calorie per degree per gram of water. So if we take a little bit of water and let's say we put it in a pan and put it on the stove and we add heat by putting a flame under it. Well, as that energy is put into the bottom of the pan, it starts raising the temperature of the water. And at 1 calorie of energy input per gram, you get 1 degree of rise. And that goes all the way up until it reaches the boiling point, right? It reaches 100 degrees C. At that point, the water will start to boil and it starts to turn from liquid to water vapor. Well, if you actually have a thermometer in the pan, you'll see that the thermometer would go up to 100 degrees C, and then it wouldn't go up anymore until all the water has boiled away. You can't make the water any hotter than that. But you're still putting lots of energy in at the bottom by burning the burner underneath the pan. And what you're doing is you're feeding that energy into the latent heat of evaporation of the water. And that's an enormous number. It's 540 calories per gram in order to convert the water into water vapor, or to convert it into steam, essentially, well, water vapor. And so you have to put all that heat in to convert it before you can start to raise the temperature of it. Now it would be a gas any higher than 100 degrees. Similarly, at the other end, if we took the same pan of water and put it in the freezer, we could lower its temperature quickly down to the freezing point, but then it would take what's called the latent heat of fusion or of freezing, 80 calories per gram in order to turn it into ice. So there's this huge sort of hump of heat that you have to get over in order to convert water from liquid to either gas or a solid. That's the latent or hidden, that's what latent means, right? Latent heat of fusion and the latent heat of evaporation. That's that energy that has to be put in or removed without changing temperature at all during those state changes. Well, what all of this means, both the high heat capacity of liquid water and then these large latent heats of fusion and evaporation, mean that the ocean is this phenomenal global thermostat, or global kind of a thermal mass that regulates the temperature of the surface of the planet. The high heat capacity means that the water holds a lot of heat in without changing temperature very much. We call that thermal inertia. The idea that the ocean has, it's sort of slow and very difficult to change the temperature a lot very quickly. It has a high thermal inertia. The latent heat of fusion and evaporation means that the heat content of the ocean can change pretty drastically without going outside this temperature range between 0 centigrade, or 32 Fahrenheit, and 100 degrees centigrade, 212 Fahrenheit, which of course the ocean never really gets anywhere near boiling in our experience. But what this does then is it actually creates this thermal mass, this heat sink for the planet that prevents, very large swings in temperature between day and night and winter and summer. And that's true for the entire planet. If we compare the Earth to Mars, Mars has night to day changes in temperature that can range up to as much as something like 150 degrees Fahrenheit. It'd be pretty awful if the noontime was 150 degrees warmer than the middle of the night. But that's exactly what it is like. That's exactly what it would be like on a planet like Earth, but without a liquid ocean on the surface to modulate all of that temperature swing. So we can see this in regional climate too. I happen to live in Madison, Wisconsin, middle of North American continent, long way away from the ocean. So that means I have summer temperatures that are relatively high, similar to other parts of the country. You know, it gets up to 90 degrees or so. But in the wintertime, of course, as everybody knows, in Wisconsin, things get pretty cold. If I look on the same line of latitude, so the same distance north over to the west coast, I reach somewhere around Portland, Oregon, or the coast of Oregon in that region. If you live in Portland, Oregon, you know that your summertime highs are not as high as in Madison, and your wintertime lows are not nearly as low as in Madison, even though they're at the same latitude. And that's, of course, because Portland is sort of benefiting, or at least is being smoothed out in temperature, by the large thermal inertia of the enormous Pacific Ocean and its heat retaining capacity that's nearby. Portland's not even on the coast exactly. It's a good distance away from the coast, but it still maintains that what we call a maritime climate, right? A climate that is modulated by the thermal mass and the thermal inertia of the very large ocean. So this happens globally and it happens regionally. Well, the thing is that this global ocean thermostat has persisted throughout geological time. For as long as the ocean's been around, because it's a basic property of the physics of water, this high heat capacity and the latent heats have kept the global ocean from either freezing solid or boiling away for several billion years. And we saw it before when we talked about the history of the ocean and the fact that it seems to have had life going on within it for all of that time. So it's an enormous stabilizing influence on the Earth's habitability. And the existence of the liquid ocean has kept the Earth's surface in the kind of comfort zone, or what we already called the Goldilocks zone, where liquid water exists, and we have to have that if we want to have life, because as we know, the one thing that all life seems to have in common on Earth is that it has to have liquid water in order to keep going and keep reproducing. Well, we do know that liquid water on our planet does sometimes turn into ice, of course. We have glaciers, we have snow, and we have frozen sea ice. We have the pack ice of the Arctic Ocean, for example. So let's take a look at the properties of ice. And this is another place where this strange polar molecule, this simple H2O molecule, has some very special properties that govern the state of everything on our planet, essentially. And that is that frozen water, ice, is a very unusual substance. Now, ice is really a mineral. You might not think of it that way, but it's simply a crystalline structure. So if we make the analogy to any rock mineral, you could say then that water is like lava, it's the fluid part, right? And the rock, the crystalline solid, is like the ice. Well, when the polar molecule H2O bonds together to form the crystal lattice structure of ice, some things happen. The main one is that the hydrogen bonds go from that interbond angle or interionic angle of 105 degrees out to 109, and that's just so that they could all interlock with each other and bond to the oxygens of the next molecule over. But the effect of this is that water expands about 9% as it freezes. So we all know that if you put an ice cube in a glass of water, the ice cube floats. Similarly, the ice in the Arctic Ocean floats on top of the water. The ice is less dense than water. Well, this makes it a really, really strange mineral. Virtually everything else on the planet, its molten form is less dense than its solid form. And so therefore, the solid crystal would sink and the liquid, the magma, let's say, would come to the top. Okay, so ice floats on water. Big deal. What does that do for us? Well, the thing is that if the ice floats on the water, then it sits on top and it creates a kind of a thermal blanket or an insulating blanket over the top of this water. So any ice that forms in the ocean is going to form on the surface, keeping the liquid water below. And this holds true for lakes and things on the continents too. How do the fish survive in a lake in Wisconsin where I live? Well, the surface freezes pretty solid, but most of the lake is still liquid water. And that's because of that density difference. If the ocean froze solid, that is to say, if ice were denser than water, then the ice crystals would sink to the bottom, they would accumulate in the ocean, more would form at the top, and pretty quickly, most of the ocean would have frozen solid, or at least in any region where there was the ability to freeze the water and send it down to the bottom of the ocean. Because the seafloor is generally pretty cold. Well, Earth would be uninhabitable. We would have frozen large parts of the ocean solid, maybe the entire ocean solid at periods in Earth's history. So again, we're fortunate that ice is less dense than water, and and basically floats on top of it. Now, water density and temperature are even stranger than that in some ways because, like most materials, when you warm water up, it expands a little bit. When I'm talking about liquid water now, it expands a little bit and gets less dense. So the density of water decreases with higher temperature. But as we get down close to the freezing point of water, it does something very strange. It reaches a maximum density at about 4 degrees Celsius, where it reaches that 1 gram per cubic centimeter density, right? That's the definition of density, is a weight per unit of volume. So 1 cubic centimeter of water, 1 milliliter of water, same thing, weighs 1 gram. That's how the metric system is actually defined. It's nice and simple. Water that's warmer is less dense, but interestingly, water between 4 degrees C and 0 degrees C is also less dense. As the hydrogen bonds start to migrate and we get the first stages of what's going to become frozen crystalline water, it actually gets just a tiny bit less dense, a fraction of a percent. And then when it actually freezes, it jumps to a significantly lower density, that 9% lower density. So water has some pretty unusual properties as a liquid and as a solid. Okay, well, what about seawater? I've been talking about pure water, but we're interested in the ocean, aren't we? So seawater, the dissolved solids, the salinity of seawater has a few important effects on its properties. First of all, the fact that you have a bunch of dissolved solids raises the density a little bit. If pure water is 1 gram per cubic centimeter, then seawater is about 1.03 or 1.035 grams per cubic centimeter. Why? Well, remember what salinity is. It's just the weight of the dissolved inorganic compounds. And so we said that was about 3.5% or 35 per mil. And so therefore, the density of water is that much higher when you dissolve that stuff in it. A second property is that the saltiness of the water acts as a kind of antifreeze. We all know that you put salt on the roads to try to keep the water from freezing. So seawater, with its salinity, freezes at a temperature of a little less than -2 degrees Celsius. And so it delays that freezing just a little bit and inhibits the formation of ice. Finally, when it actually does reach that temperature and starts to freeze, the freezing of seawater excludes all that salinity, all those dissolved solutes. So you freeze seawater, you don't get frozen ocean water, you get frozen fresh water. It's almost like a distillation process. It gets pure water, pure frozen fresh water. Well, that means what it leaves behind is all the solutes that were in that bit of the water. So the still liquid water that's adjacent to that frozen bit is now higher salinity. It's more of a brine. And if it's more saline, it has more dissolved solids, and therefore it's denser water. So it's water that has a little bit higher density than the other water in the ocean around it. Well, that brings up the question of what's the importance, in fact, of the density of water. Well, like most substances, as I said, seawater expands and becomes less dense as it warms. And so it also becomes more dense with a little bit of salinity or with a little bit greater salinity than otherwise, than fresh water. So the density of water varies over relatively small amounts, just a few percent, but it varies with temperature and with saltiness or salinity. Well, it turns out that the density of that seawater controls a great deal, as we're going to see, about the structure of the water column, and in particular, the layered structure of the pelagic open ocean. We have near surface water and then water down to the average 4-kilometer depth, and it has density variations in it. Let's look at those in a little bit of detail. Basically, ocean water forms these stable layers by density. We say the ocean is stratified by density. And there's a surface zone, and then there's a deep zone, and there's something in between. So the surface zone is a region where waves and currents keep things pretty well mixed together, and so there's pretty uniform density property. But the surface zone water tends to be low density. It's low density because it's warmed by the sun. It's low density because of the input of fresh water, perhaps from rain and from rivers. But mainly it's low density because lower density water will rise and higher density water will sink, just like hot air rises and cold air sinks for the same reason. So the surface water is the least dense, and it's all mixed. The deep zone, something like 80% of the volume of the ocean, the zone that turns out is below several hundred to about 1,000 meters or so, is pretty cold and it's not moving very fast because it's not stirred up by the waves and much by the wind and ocean currents. And so it's a mass of relatively dense cold water with that standard seawater salinity. Well, in between the surface zone and the deep zone then is a region that's called the pycnocline. Now, pycno is a word root that just relates to density or weight of something, and then a cline is like an incline, it's a gradient, right? So the pycnocline is the region that just is the sharp gradient or the depth zone over which the gradient in density changes relatively rapidly in the ocean. And the pycnocline is in different depths in most of the world's ocean, but it starts at about 100 or a couple of hundred meters down and extends down to maybe 1,000 meters or so, as I said. But it's a strong density gradient. Now we know that saltwater, seawater, has a density that's governed by salinity and by temperature. So both of those things actually affect the density, and therefore the pycnocline is reflected as a gradient in all of these other properties as well. The most important one and the most directly measurable one is what's called the thermocline. Okay, thermo, so heat related. So I'm talking about the depth zone of a strong temperature gradient. The pycnocline is also very typically a thermocline. Near surface waters are warmer, they're relatively well mixed, they go through a big gradient over a few 100-meter range, and then the deep ocean is not quite uniform in temperature, but pretty close. And in fact, the temperature of the water in the deep ocean is from just 5 or 10 degrees C normally down to about 1 or 2 degrees C, or near the polar regions even actually slightly below zero, again because of that antifreeze property of the salinity. Well, if there's a thermocline, then there's also a salinity incline or a salinity gradient. And the name we give that is the halocline. Maybe you've heard that the geological name for salt is halite, H-A-L, another root that means salt. So a halocline is the salinity gradient in the water column. All of these things are a reflection of the same property, that the density is lower at the surface, it's fairly uniform at depth, and there's a steep gradient that kind of separates the ocean into a surface zone and a deep zone. And this is going to have huge implications for ocean currents, where life lives in the ocean, and the stirring and mixing in general of the ocean as a whole. So fundamental property of physical and chemical oceanography is this separation into surface zones and deep zones with an intermediate steep gradient in all of these properties. Well, if we look at the thermocline, we can actually see that the ocean has a strong thermocline, but it varies a lot depending on where we are on the planet. And we're going to return to this story a little later on in the course when we deal with temperature zones on the planet. But basically, the thermocline is very strongly developed in tropical regions. As you might imagine, the surface waters are very warm, but the deep water is still cold, even in tropical regions. So you have this very strongly developed large thermocline, and along with it, a pycnocline. In temperate regions, it's sort of intermediate, and then in polar regions, the surface water is cold, and so is the deep water, so the thermocline is not very pronounced. Well, let's take up another physical property of water, and this one's pretty easy to deal with. That's pressure. Okay, pressure increases with depth in the ocean. No surprise, right? Pressure is just a function of the weight of the medium, the fluid medium that surrounds you. So we're standing here on the surface of the Earth. Of course, we're under a pressure of 15 pounds per square inch. Everybody knows that. And that pressure comes from the weight of the atmosphere, actually the physical weight of the gas, the air, above our heads. Now we're under that pressure here at the surface. 15 pounds per square inch sounds like a lot. If you put a 15-pound weight on your hand on 1 square inch, it would be quite a compression. But of course, we don't feel it because we have that pressure inside our bodies as well as outside of our bodies. Well, gas, the atmosphere, is not very heavy. It doesn't have much density. But the ocean has a lot of density. It has that 1 gram per cubic centimeter. That's 1 kilogram per liter of water. And that means it's 1,000 kilograms, essentially a ton for a cubic meter of water. A cubic meter is not such a big thing. So water is incredibly heavy. And what it means is that the pressure increases as you go down in the water about 1 atmosphere, 1 equivalent of that atmospheric pressure for every 10 meters you go down in the ocean. Now, that means that at the average depth of the bottom of the ocean of, say, 4 kilometers, we're at 400 atmospheres of pressure. Well, a human being, let's say scuba diving, can stand to go to a pressure of maybe 3 to 4, a little bit more atmospheres for the really extreme divers, but that's it. Our bodies have gases inside. Our lungs can't inflate anymore at higher pressures than that. We're not compensated for the pressure around us once we're in the water like we are in the atmosphere, so we really feel it. If you want to go to a higher pressure than that, you need a pressure chamber, and that means you need a submersible like Alvin. So when I told you about getting into the Alvin submarine and going to 2.5 kilometers below the sea surface, I certainly wasn't under the pressure at the bottom of the ocean. The submarine itself was under that pressure, and that pressure chamber was keeping that pressure off of us, fortunately, or we wouldn't have survived. Well, I'd like to take up finally then the last piece of this, the sort of story of the physics of ocean water, and that's the penetration of light into the ocean. And we've already said that, well, one of the problems with mapping the seafloor is that light doesn't go through the water and can't, be used to image the bottom, and not even radar or other forms of electromagnetic radiation get through water. So we can ask the question, it's kind of like, why is the sky blue? Well, why is the ocean blue? And why do we call it the deep blue sea? Well, light penetrates the ocean water to a certain degree, and we certainly have a zone of the ocean that's lit up, and we call it the photic zone. If you go down to some depth in the water, you still see light, of course, coming through the water. But it's typically a very shallow zone. You start to see changes even just a few meters down. By 100 to 250 meters, maybe in the absolute clearest water parts of the ocean, up to maybe 500 or 600 meters, there's detectable amounts of light penetrating, but no deeper than that. And of course, the ocean is 4,000 meters deep or more on average. So most of the ocean is the aphotic zone, as we've already discussed. Within the photic zone, light is absorbed by, again, the polar properties of the water molecule. And the energy, the wavelength of the light is coming in, and it vibrates those molecules, and they absorb and scatter the wave energy of the sunlight. They do this differentially. They differentially absorb the light by color. And because each color of light in the spectrum has a slightly different wavelength of the light radiation, and so therefore they affect the water molecule differently. So it turns out that if we looked at kind of a spectrum, the light that's most rapidly absorbed are the reds and the oranges, the things at that end of the wavelength scale, and it's the blues and greens, but especially blue light, that penetrates the farthest into the ocean. So there's differential absorption of different colors. Blue penetrates the furthest, and so it's backscattered from the water, and so that makes the water look blue. All the other light has already been absorbed and doesn't penetrate as far, and therefore we don't see as much of it when we look down into the water. Now, the light penetration into the ocean exponentially declines with depth. So by only 1 meter depth in the water, only about 45%, less than half of the light that's shining on the surface, has reached that 1 meter depth. Only about 16% or so of light has made it to 10 meters, and only 1% or less is making it to 100 meters, even in the clearest water where it doesn't have a lot of particles and things like that in it. So if we look at the light in the ocean, we can see it really graphically. Just look at a tropical fish swimming on a reef, maybe only a few meters down in the water. And if we photograph it in the ambient light that's present at that depth, the light is mostly blue wavelength only, and it's really got a deficit of color in it. We flash a electronic strobe, so we get a full spectrum light on that, and we see all the different vibrant colors of that organism. And in fact, many of those tropical reef fish and other organisms have evolved to have brilliant colors on them to sort of compensate for the fact that the light that they're in doesn't really show those brilliant colors to their full degree. So we call it the deep blue sea, right? But if you go and stand on the beach and you look out at the water, usually it looks kind of green, sometimes kind of brownish even, and maybe gray, but really not the sort of kind of vibrant blue that you're seeing in this photograph that I actually took over the side of a ship out in the middle of the ocean. And well, the difference, of course, is the particulate matter that's in the water. So Anywhere you're on the coastline, you're looking at water that is over the continental shelf. The shelf is pretty far offshore. It's maybe in breaking waves and things like that. So it's got a lot of mud and also algae or phytoplankton and things like that mixed in, making it green. But when you get well offshore, especially off the continental shelf into the deep water, the ocean really is a vibrant and brilliant blue. And no, I haven't modified the colors of the image that has this fish swimming in it. It's actually a mahi-mahi. That's what the real, true, deep blue ocean looks like virtually anywhere you go on a sunlit day. So we've seen in this lecture and the previous one that in many ways water is the defining physical substance for life in the surface environment on Earth. And it's really the special properties of water, our luckiness that Earth just happens to be the liquid water-bearing planet because of its distance from the sun, because of its initial composition, and because of its amount of gravity that held the water here, that has maintained the Earth the way it is. And that includes the heat-retaining capacity of water, the density of water, and the special properties it takes when it freezes, and how it transmits light. Those are all things that control oceanic processes, and we'll be looking at many of those processes controlled by water over the course of the next few lectures. And finally, I just want to kind of leave us with the fundamental thought that the ocean is the Earth's great heat sink. Those heat-retaining properties are maybe the most important ones of all. It's kept the entire planet in this narrow, very narrow really, temperature range, hospitable to life for literally billions of years.